Welcome to the Module 4 Input-Output Analysis. Now we're going to solve an input-output model, and we're actually talking a little bit about the Leontief Inverse. If you recall Leontief, he was the person who came up with the whole idea here, and I give you some brief background in the first video of Module 4 here. If you recall the last video, we have the economy written into a matrix notation. We have in the matrix the intermediate consumption, we have final demand components, which we will label X. We have value-added components, we have imports, and we have total output and inputs, which are X. So, da war jetzt gerade ein Riesenfehler drin, ne?
Ich meine auch das F, da hatten Sie schon
ja, genau.
Also fangen wir mal von vorne.
Ja. Welcome to Module 4 Input-Output Analysis. After we looked into the structure of an input-output table, we're now going to look at the Leontief Inverse. The Leontief Inverse is a way of solving the input-output model. If you recall the last video, we set up the economy in matrix notation. We have there the intermediate consumption, which is the set values, the sector 1 to 3, the good flows between them. We have labeled that in gray. Then we have final demand components. This is F labeled. This is all the stuff that leaves the economy. You recall household consumption, governmental consumption, all that stuff. We have value-added components, wages, profits that flow into the economy, or not flow into the economy, but actually allow the production of goods and services. We have imports. These are the things that flow into the economy. And we have total outputs and inputs labeled in X, which is the stuff that is the complete output that the economy is capable to produce. If we look at this matrix notation here, the input-output label requires stock flow consistency. So we have the goods flowing into the economy, within the economy, and everything, output and input, has to be equal. So this forces the fact that final demand components here in yellow must be equal to the sum of the value-added components and the inputs. Otherwise, the equation wouldn't hold. So this is a fact that we can actually make a lot of use of when we solve bigger problems in input-output modeling. We use final demand components. We went over this in the last video a little bit, but here now again, this is household consumption, government consumption, exports, and the net inventory changes. So the stuff a company has on their shelves. Value added and imports are wages, taxes, raw material, and depreciations, and of course inputs itself. So the container that arrives in a harbor from a different country, things you purchase in a different country and bring back over the border, all that stuff counts into imports. And the way to solve input-output tables is a little bit more complicated than just looking at stuff. We need a technical coefficient matrix, which we label A. It captures the intermediate consumption, so all the set parts, and it is the input from each sector that is coming from another sector over the total output of that sector that sends the stuff to the original sector. So we kind of transform the set matrix that we had into an A matrix by making things more relative compared to the total output of a specific sector. So in columns, we now have the input structure for the production in a given sector. And in the rows, we have how the output is distributed as inputs across all sectors. So we can, for more easily, trace relative input shares throughout the economy. And if we want to solve the input-output table in a way of like, what is the total production of an economy given input factors, we know that the total output must be equal to the intermediate consumption, so all the goods that are flowing in the economy, which is this technical coefficient matrix multiplied with the total output. and we add to that the final consumption. This can be easily solved for x to determine the output, where we have to shift things around, get the inverse of the identity matrix minus the technical coefficient matrix, and then we have the total output of the economy. And this identity matrix minus the technical coefficient matrix, and of that the inverse, is called the Leontief inverse. The Leontief inverse matrix is invertible, so only if the largest eigenvalue of the technical coefficient matrix is less than 1. This sounds like, oh, arbitrary, but it also makes sense. This is one of the cases where economic meaning beats mathematical possibilities, because it requires an economic interpretation here. It is not possible that a sector can consume more than it will produce in the output in the long run, which means a sector is only able to sell what it has produced in the past. We cannot sell more than we actually produce. This is a really, really important aspect, and this is something where the economic understanding helps you to catch errors, perhaps, in your Leontief inverse. If you realize that the largest eigenvalue is more than 1, you already know something's fishy here and there must be a mistake. We label the Leontief inverse quite often as B, just because so we don't have to write the identity matrix or the inverse of the identity matrix minus the technical coefficient matrix. Now, with B, we have also the elements Bij in the Leontief inverse, which represent the total output from sector I, which is required to meet 1 unit of final demand of sector J. So this is again where the relative aspect plays in. And we can include direct effects where we have the immediate input, so you actually need this input to produce something. It comes to the company, they put it in their production black box, and something else comes out. And we have also indirect effects, so inputs that are needed to produce that input. These are aspects that we can trace through the economy, where everything, all the origin comes from. The Leontief inverse, therefore, has also multiplier effects. We can have sectoral interdependencies which amplify initial shocks. If you shock one specific sector in the economy, this shock can flow through the economy and have impacts on complete different sectors. And we can also identify bottlenecks. Here, sectors with a high value in the Leontief inverse are really critical for the economy, because those are the ones that this sector requires a lot of input of. So just by relatively comparing the input origin, if one sector depends to 90% on another sector, well, that sector is extremely crucial for the other sector, because 90% of its output depends on its inputs from there.